Hello and welcome to our lesson on solving exponential equations with common bases. In this particular module, we will be doing a lot with exponential equations, functions also, and then what we call logarithms, and hopefully you'll understand the connection between all of it when we get to the end. So lots of different exponential equations we're going to solve, but in this particular lesson, we're going to focus on exponential equations that have common bases. So before we get started, what does it mean for an equation to be exponential? Well, you might be thinking an exponential equation is going to have an exponent, right? And that's going to be true. But would that make an equation like x squared equal 4? Would that make that an exponential equation because that equation has an exponent? No, in fact, we should know that that is a quadratic equation, or if we had an x cubed equals 8, that's a cubic equation. So the fact that it has an exponent is part of it, but something has to be true about the exponent in order for it to be exponential. If the equation is exponential, then the exponent in the equation is the variable. So instead of x squared equals 4, maybe it's 2 to the x power equals 4, right? Or instead of x squared equals 9, it's 2 to what power equals 9 or something like that. So you have an exponent in your equation, but your exponent is your variable. It's what you're going to be solving for. So an equation is exponential. It is exponential if the variable in the equation is an exponent. So we want the variable in your equation to be your exponent, and that's what's going to make it exponential. And the same for functions when we get to those. Okay? So 3 to the x power equals 9 is an example of an exponential equation. And I would hope and argue that you should be able to tell me the answer to that equation without me teaching you anything about the solving process. So 3 to what power equals 9? Hopefully you all can see that the answer has to be 2 because it's 3 squared that makes 9. But what I want to show you is the idea behind what we're going to do to solve equations that look like this particular equation. The reason we know this answer is because we know that 9 is the result of 3 squared. Okay, we know that there's a base in common here. The goal is going to be to take an equation that looks like this one, or something a little more complicated, and rewrite both sides with a common base. So for example, the base of the exponent on the left side of the equation is a 3. And the goal would be to take the other side of the equation and write that number, if possible, with the same base. So rewriting the 9 as what we know, which is 3 squared. Because if we have 3 to a power on one side and 3 to a power on the other side, those bases no longer matter, right? If 3 to a power on one side has to equal 3 to another power on the other, don't those powers have to be equal? If the bases are equal, the powers would have to be equal as well. So if we can get these bases to be the same, they basically don't impact our equation anymore. We can cancel them out. They don't matter. Our solution will be found using just the exponents. The exponents have to be equal if those bases are equal. So the goal is going to be to try to get those bases to be the same. It's to look for a common base on both sides of the equation, because once the bases are equal, they no longer impact our equation. So we can sort of just get rid of those and solve using just the exponents. Okay? So the goal, again, is going to be to do some rewriting. Now I just want to clean this up a little bit. So we knew x was 2, and just so we could look at this differently, we knew it was 2 because we knew 9 was 3 to the second power, and that meant that x had to be equal to 2. Okay, that exponent had to be equal to 2. So we're going to be looking for some common bases, but obviously not all the equations will be as simple as this one, otherwise we wouldn't need a process. Just so that we have a list handy, we're going to make or fill out this chart here to fill out a bunch of powers, okay? The process that we're going to be looking at today requires us knowing various powers of various bases, and just to put these numbers on the radar for you and to make sure you're kind of seeing them, we're going to make a little list to have this handy. So I put bases in this column here, and then the powers we want to raise them to in this row. So for example, in this first box right here, I'm looking for 2 raised to the power of 2. So 2 as my base raised to my power of 2 is going to be 4, and then 2 to the third power would be 8, and then 2 to the fourth power would be 16, and so on. So 2 to the fifth power is 32. 2 to the 6th power is going to be 64. 2 to the 7th power is going to be 128. And then 2 to the 8th power is 256. So the powers of 2's go pretty high because those numbers are manageable. Notice that we have a bunch of grayed out area here. It's not that those powers don't exist or aren't helpful. It's just they don't come up as much in our equation. So what I'm doing here is creating a list for you to have handy of powers that you're going to see, or bases that you're going to see quite a bit. Okay, so let's continue here. 3 to the power of 2, or 3 squared, is 9. 3 to the power of 3, or 3 cubed, is 27. 3 to the 4th power is going to be 81. 3 to the 5th power is going to be 243. And those are some pretty common powers of 3 that will occur in the problems we're going to look at. And that was really sloppy, 27. Try that again. Okay. And powers of 4. So 4 squared is 16. 4 cubed is 64. 4 to the 4th is, let's see, 16 times 16. I think that's 256. Let me just make sure. 4 to the 4th. Yeah, 256. Okay. Sometimes I can't remember. All right, so powers of 5. We have 5 squared, which is 25. 5 cubed, which is 125. 5 to the 4th power would be 25 times 25, which is 625, is going to go there. And then we have some powers of 6. 6 squared is 36. 6 cubed is 216. And then 6 to the 4th power, I think, is 1,296, but let's just double check that. So 6 to the 4th, yeah, 1,296. Then we have 7 squared, which is 49. 7 cubed, which is 343. And then 8 squared is 64, and 8 cubed is 512. And then 9 squared is 81, and 9 cubed is 729. And then 10 squared is 100, 10 cubed is 1,000. Those are the easy guys, right? 11 squared is 121, 11 cubed is 1,331. 12 squared is 144, 12 cubed is 1,728. And then 13 squared is 169, 14 squared is 196, and last but not least, 15 squared is 225. Okay, so there are other powers that could occur, but these are some really common ones that we're going to see, so it'd just be nice to have this list handy, or at least to have these numbers on the radar. So what I mean is, when you see, for example, an equation that has the numbers, let's say 256 and 16, what it would be ideal is for you to recognize that 256 and 16 are both powers of 4. Or you could say that 256 and 16 are both powers of 2. So this would be the common base we would be looking for. Or, get rid of those messes. Let's say you're looking at, I don't know, 729 and 81. Okay, recognize those are both powers of 9. They have a common base of 9. Or you're looking at, I don't know, 125 and 25, and recognizing those are both powers of 5, so they have a common base of 5. So we want to be able to try to recognize these as what base they come from. Recognize 125 came from raising 5 to the power of 3, and that 25 comes from raising 5 to the power of 2. Okay? So that we can rewrite these numbers with the common base and get those bases to cancel. So we want to try to find a common base for the expressions on each side of the equal sign, and rewrite each side as a power of that common base. And once those bases are equal, I'm going to say they cancel. They aren't technically canceling out of the equation, but they no longer impact our equation. So I cross them out just so that we can ignore them. Okay, so they no longer impact the equation. I'm going to say they cancel just for short wording here, but technically they're not going anywhere. They just don't affect our problem any longer. The key is, once they're the same, the exponents have to be equal. So we're going to solve using the exponents. We're going to set the exponents equal to each other to solve. And the good thing is here we can always check our answers, and we check answers to equations by plugging them back in. Okay, so let's try this out. Here, for example, it's not as easy to see 3 to some power equal to 9. I know the power has to be 2. Now, this isn't that challenging yet, but still more challenging than the original equation we looked at. Now, hopefully you're recognizing that 3 and 27 are both powers of 3. So the goal would be to make both these sides or to rewrite both these sides with that base of 3. So the left here already has a base of 3, which means I'm just going to leave it alone. But on the other side, 27 is 3 to the third power. So I'm going to rewrite 27 as 3 cubed instead of leaving it as 27, because now both sides have the same base, which means these no longer affect our problem. So we can solve using just our exponents. If these bases are equal, those exponents have to be equal as well. So we're going to take our exponent of 2x and make it equal to our exponent of 3. And now this is the equation that we're going to solve to get our answer. So we're going to divide both sides by 2. And that means x has to equal 3 halves, or 1.5, or 1.5. Okay? And you don't need to do this every time, but if you wanted to check your work, plug it in. So 3 raised to the power of 2 times 3 halves was what we got there. Should give us 27, and you can see when you plug it in fact does. Okay? So let's try that again. So we have 125 and 25. Hopefully we're recognizing 125 and 25 are both powers of 5, right? And if you need to, you look back at the list and go, okay, here's 125 and 25, both powers of 5. So I'm going to take the 25 and make it 5 squared. I'm going to take the 125 and make it 5 cubed. Okay? I'm making a mess of my paper here. So we're going to rewrite this. 125, again, is going to become a 5 cubed, and I have an x there that I don't want to lose. Okay, so 5 cubed, and then I'm just going to bring the x down. So all I did was change this 125 to 5 cubed. And then on the other side, 25 is a 5 squared. Okay, now that those bases are the same, they don't impact the problem anymore, so we're going to solve using just our exponents. So we have 3x here that has to equal the 2 that's on the other side. So 3x is going to equal 2 because these bases no longer matter. So all we need to do to solve is divide both sides by 3, and we can see that x has to equal 2/3. So 2/3 is our answer. So if I take 125 and I raise it to the 2/3 power, I do in fact get the 25 that I have on the other side. Okay? Alright, one for you to try. If you're feeling so far so good, pause the video and give it a shot. Otherwise, we're looking for a common base for 16 and 256. So 16 and 256 actually happen on two lists. 16 and 256 we can rewrite as powers of 4, or 16 and 256 can be rewritten as powers of 2. Either way, you're going to get the same answer. So we have options for common bases. I'm going to use 4, although it doesn't matter. You can also use the 2. I just like 4, so I'm going to use 4. So I'm going to change the 16. The 16 is going to become 4 squared, and then I still have that being raised to the power of 3x, so I don't want to lose that. And then on the other side, 256 is 4 to the 4th power. Now that those bases are the same, I can ignore them. The exponents have to be equal as well. So the 6x that I have on this side has to equal the 4 that I have on the other side. So dividing both sides by 6, I can see my answer, which is 4/6, or 2/3 when we reduce. So 2/3 is our answer once again. Okay? Same kind of deal here. We just have to be a little more careful when our exponents have multiple terms. I'm going to show you why. So 4 and 32. 4 and 32, we can see here, are both powers of 2. 4 is going to become 2 squared, and 32 is going to become 2 to the 5th. So I'm going to rewrite 4 and 32 as powers of 2. So this becomes 2 squared. 4 is 2 squared, and it's being raised to the x plus 2. And then on the other side, 32 is 2 to the 5th power. So now my common bases no longer impact my work. But here I have to make sure that I distribute the 2 to the x and the 2. So if I have multiple terms in my exponent, make sure that you distribute that power. So what I'm looking at is 2x plus 4 equal to the 5 that I have on the other side. So now I have to subtract 4, which means that 2x has to equal 1. And then lastly, divide by 2, which means here that x has to equal 1/2. Okay, so 1/2 is going to be my solution there. And again, if you want, just check it. Really easy to check, especially if you have your calculator handy. 4 raised to the power of, I said 1/2, right? So 1/2 and then plus 2, and it does in fact get me the 32 that I have on the other side of the equal sign. Okay, moving right along. 49 and 3, 43, both powers of 7. So we're going to change this 49 to 7 squared, and then don't lose your x minus 1 power there. We're going to change 343 to 7 cubed, and don't lose your x plus 2 power there. So these bases no longer matter. We're going to solve using our exponents. So 2x minus 2 on this side, 2x, I swear, I changed to blue. 2x minus 2 on this side, minus 2, and then 3x plus 6 on the other side. 3x plus 6 on the other side. Those exponents have to be equal because those bases are equal. So let me get the x's together here, subtract those two over. That leaves me negative 2 equal to x plus 6, and then I can solve for x here by subtracting the 6, and that leaves me with let's see, negative 8 equal to x. So x is equal to negative 8. Okay? Again, if you're feeling all right with this so far, this would be a good place for you to pause and make sure you're doing okay. So 8 and 16, careful, not both powers of 4, but they are both powers of 2. 8 becomes 2 cubed to the 2x, and then 16 becomes 2 to the 4th to the x minus 4. So we're going to be looking at 6x on this side equal to 4x minus 16 on the other side. 4x minus 16 on the other side. So I need to get these x's together to solve. Those cancel, and so now I have 2x equal to negative 16. And then dividing, I coincidentally end up with the same answer we had in the last one, which is a negative 8 again. Okay, and again, if you want to check your work, since we have variables on both sides, we'd have to plug in twice here. So 8 raised to the 2 times negative 8 power on that side gives you that crazy decimal. As long as we get the same crazy decimal on the other side, then we're good. So 16 raised to the, this would be negative 8 minus 4, and there it is, matching crazy decimals on both sides of the equal sign. Okay? Alright, so in the next couple, we're going to have to apply an exponent rule, and I don't know if we've seen this one in a while. So we can see, hopefully, the common base for 6 and 36 is 6. But if I rewrote this side, let's say I leave this side alone, okay? If I rewrote this side as 6 squared, that doesn't really help me because this is 6 over 1 here and 1 over 6 here. So what do we want to do? We want to apply our negative exponent rule, but in reverse. So normally if we saw 6 to the negative first, that would be 1 over 6 to the positive first. If you remember, the negative exponent rule means that the base of that exponent is on the wrong side of the fraction. So when we have something with a negative exponent, it's supposed to move to the opposite side of the fraction. So normally, we have a negative exponent, like 5 to the negative 2, and we move it to the bottom of the fraction to make that exponent positive. But in this case, what we're going to want to do is work in reverse. So right now, for instance, this 6 is on the bottom of the fraction with a positive exponent. What I would do is move it to the top of the fraction, give it a negative exponent, and that way our bases would be the same and they could cancel. So if you need to move your base to the other side of the fraction, like it's on the bottom here and it needs to be on the top so it matches the other guy, you're going to change the sign of the exponent, right? Changing the sign of the exponent is how we change the side of the fraction that base is on. So we are going to get rid of all this mess and make a little note here. And this all zoomed. Okay, so changing the sign. Change the sign of the exponent to change the side of the fraction, or to move the base to the opposite side of the fraction. Hopefully that makes sense, what I wrote there versus what I'm trying to do. Change the sign of the exponent to move the base to the opposite side of the fraction. So what's going to happen here, again, so this is going to be 6 to the positive 1 here, and what we're going to do is make this 6 to the negative 1 with our power of x. Right? And just, again, just to confirm, just to be extra safe here, if you had 1 over 6, that's the decimal. If you raise 6 to the negative first power, same decimal. So 1 over 6 to the positive 1 and 6 to the negative 1 have the same value. So I didn't change anything. I just moved the side of the fraction it was on. And when we do that, we change the sign of the exponent. So we have 6 to the negative first on one side, and then 36 becomes 6 to the second on the other side. Because now we have the same base on the same side of the fraction, we can ignore those. So what we're going to be solving with here is the negative x, and it has to equal the 2 that we have on the other side. So just dividing both sides by negative 1, we know that x has to be equal to a negative 2. Negative 2 is going to be our answer. Okay? Let's try that again. So 81 and 729 are both powers of 9. This is 1 over 9 squared here to the x, and then this is 9 cubed to the 2x plus 1. But again, I can't cancel those bases because the 9 squared is on the bottom of the fraction and it needs to go to the top. So this is going to become 9 to the negative 2 to the x, and on this side I'm going to leave my 9 cubed and 2x plus 1. Now my bases are the same, and they're on the same side of the fraction. Now I can ignore those bases. So we have negative 2x on this side equal to a 6x plus 3 on the other side. 6x plus 3 on the other side. I'm going to get these x's together, so let me subtract these 6 over. That leaves me with negative 8x equal to 3. And then my last step to solve is dividing both sides by negative 8. Those reduce, and so that leaves me with x equal to a negative 3/8. Okay, and that's kind of a weird equation, right? Let's just double check to make sure. If I take 1 over 81 and I raise it to a power of negative 3/8, that's what I end up with. Now on the other side, I should end up with the same thing. 729 raised to the, let's see, 2 times, I said negative 3/8 was the answer, and then a plus 1. And there it is. We're confirmed, about 5.2-ish, the same decimal on both sides of the fraction when we plug that answer in to verify. Okay? All right, let's try this guy. So this is similar here. We can see hopefully the common base for 100 and 1,000 is going to be 10. So I have 1 over 10 squared here. And then I have 10, sorry, this was 10 cubed. 10 squareds on the other side to the power of 3x. So I can't cancel the 10s yet because the 10 cubed is on the wrong side of the fraction. So this is going to become 10 to the negative 3 to the x. And then, that's so sloppy. And then this side can stay for a second here. So 10 to the positive 3 on the bottom becomes 10 to the negative 3 on the top of that fraction. Now our bases are the same. They're on the same side of the fraction, which means now we can ignore those bases. So we're going to solve with a negative 3x on this side and a positive 3x on the other side. So a negative 3x equals positive 3x. So sometimes these equations that are a little bit easier to solve we tend to struggle with, but we would do the same thing here that we did, let's say, here. Okay, if I have x's on both sides of the equation, I want to move them to the same side of the equation. So let's say I choose to move these guys. Let's say I move these 3x's over. What does that leave me? It leaves me with a negative 6x on this side and nothing on the other side, which is a 0, which allows me to continue to solve if you couldn't already see the solution. 0 divided by negative 6 means 0 is going to be our answer here. Hopefully it makes sense. That was the only number that we would be able to plug in to make both sides the same there. So 0 is going to be our solution. Okay? And then one last one. If you feel like this is something you can try, pause the video and give it a shot. Otherwise, the common base for 12 and 144 is 12, right? This is 1 over 12 to the first. And 144 is 12 squared. So this becomes 12 squared to the x minus 3. Well, instead of leaving that 12 to the first on the bottom of the fraction, 12 to the positive 1 on the bottom becomes 12 to the negative 1 on the top of the fraction. And now that we have the same base on the same side of the fraction, we can ignore these bases. So it's going to be negative 4x on this side equal to 2x minus 6 on the other side. And I'm going to get these x's together by subtracting these two over. And so I have negative 6x equal to negative 6. And then dividing both sides by negative 6, I get my answer, which is x equals positive 1. And just for good measure, let me verify that that is correct. So I have 1/12 on this side. And I'm going to raise that to the 4 times, nope, need parentheses here. 4 times, the answer was 1. I guess I don't have to plug the 1 in, but I get that decimal. Let me confirm that the other side gives me the same decimal. So raising it to the 1 minus 3 power, and yep, same decimal on both sides, so it's confirmation that x equals 1 is my correct answer. Okay, so exponential equations with common bases. The goal is to get that common base to make those cancel and solve with the exponents that remain. Won't always be possible, so as we move through the module, we'll look at some other ways to solve, and then in fact, if you don't like this method, I'll show you another, but I think you're going to like this one over the alternative. In any case, you have some practice problems to work on, so give those a shot, and if you find yourself struggling and needing some extra help, then just reach out. All right, guys.